Okay, everybody, I'm Kyle Adams. I'm an application specialist for SLM Solutions. Today we're going to be talking about selecting parts for additive manufacturing. So this is actually a really interesting topic because 2 years ago, SLM Solutions was in this particular booth, and the big question was, what do you guys do? This year, the question is, what do I build and how do I make your product viable for my company? So market's definitely moving, we're definitely moving up, and we're becoming a what is this to what are we doing with this, and in 2 years time hopefully everybody's going to have one of these systems, and how do we make this better? So SLM Solutions, we're a company out of Lübeck, Germany. The machines are made there. This is our new headquarters and facility. 250,000 square feet. We have the capacity to build up to 1,000 machines a year, and we can actually expand this as well. This is our US headquarters. We're based out of Wixom, Michigan. There we have 4 machines in the lab that I manage here. SLM 500, 2 280s, and a 125. There we do benchmark builds, customer support builds. We have an applications team, service team. Sales are all local sales, so they live in the region that they work. And we also have a warehouse for spare parts and storage. These are the 3 machines that we provide. So there's an SLM 500, SLM 280, SLM 125. Really intuitive. The 500 is a 500 millimeter by 280. The 280 is 280 square. And the 125 is 125 millimeters cubed. There's also an SLM 800. It's exactly the same XY as the SLM 500, but it's 850 millimeters deep. It was designed for the oil and gas industry to build long, tall parts, but we're finding multiple other uses for it. So some of our key areas: automotive, aerospace, energy, tooling, and healthcare as well. Healthcare is definitely taking off, but really right now we focus on the energy and aerospace market. It's really what we got into initially, and it's really taken off. So we're trying to build parts that are high value, low production parts that really couldn't be manufactured in any other way. Here we have a handful of parts. Some of them we'll go into later in detail, but we have aerospace components, oil and gas components, and if you look at some of this stuff, it would be either really hard, time consuming, or impossible to machine with traditional manufacturing. Some of the advantages. So we have freedom of geometry. We can build anything that we want. That being said, I always say you can build whatever you want, but it doesn't always mean it's going to work. If we take a direct casting with internal passageways that's not designed for additive, it may not work. And these are all the things we're going to have to take into consideration when we're selecting parts for the additive process. Some of the indirect things: we can reduce weight. We can make automotive and aircraft parts that are typically 5, 6, 7, sometimes 30 pieces and combine them into one individual piece. That way we're reducing the amount of machining needed, reducing the machining cost, and so on and so forth. The SLM process. So this is how the process starts. We take our 3D model, we're going to put it into the support software, we're going to support that model, we're going to then slice it. This is our XY G code, laser speed, laser power, laser pathways. Once that's done, it's going to export and then be imported into the machine. From the machine's going to read it and then be able to build our pieces. This here is a camera view of the SLM 500. Right now it's building with 4 700-watt lasers. You can see that the recoding process happens. Lasers are going across their pathway. They're going to continue to build. Once the part is complete, it's then going to recoat and travel to the back. So we have a 75 micron spot size. A typical build thickness is 30 micron layers. This allows us to get very high resolution pieces. We can also move up into 60 or 90 micron layers. This is how we get speed out of these systems. Thicker layers, faster build times. You also see that we have bidirectional recoding. So every time the recoder moves, we're laying down a layer and building a part. There's no wasted time for recoder travel. So I like to consider the 7 attributes of building an additive piece. Those 7 attributes: size. Does this piece fit? Materials. The material you want to build with, does it weld? This is a welding process. Number 3, economics. Is there value in using metal additive? Performance. is the performance of the material out of the machine met by what performance callouts that you require for your piece? Qualifications. Is it yours? This is actually a fairly common thing. A part can't just be made in additive because you want to. It needs to be designed for additive and called out for additive. Design. Will the design work? Is there passageways that need to be supported? Is the design going to be functional out of the additive process? And then post-processing. Is it painful? This is not a very simple process to remove supports. Is it going to be painful for you guys to get the supports out? So first one, does it fit? This is a typical SLM 280 build plate. You can see that the actual plate's only 278 millimeters square, and you have the bolt hole covers in all four corners, so you do lose some area. But you have a 365 millimeter deep. You know, this is the typical standard mid-sized machine size. Pretty basic one. Does it weld? Material. So this isn't just a micro welding process, like I said. These are our basic materials. So we have aluminum, cobalt chrome, Inconels, titanium, and then tool steels and stainless steels. That being said, we do have an open process, open machine, so any material that you can get sourced, you can add to the SLM system and run. All it needs to do is pass morphology and particle distribution for flowability, but we have all those specs provided. But these are the main basic materials that we do provide. Economics. Is there value in what we're trying to build? So, part cost illustration. We do part modeling. We can actually control this fairly well. We know how much energy the machine's using, how much it's going to cost for us to run it, how much material we're going to be using to build, and how much the material is going to be waste as well by support material. We include also waste because the welding process produces soot and condensate. That's going to be lost material. It's about 2 to 4% per build. Everything else that isn't welded is 100% reclaimable. This is a nice little thing. So each machine is capable at a fairly decent uptime about producing about a ton of material a year. So whether that's a lot of small parts creating a ton of material or just a few very large parts creating a ton of material. But more or less an SLM machine should be able to produce a ton of material per year. So we have to decide how much you actually are wanting to make and how many machines you need to reach those numbers. So for example, this is a SLM 500. These are keys, size of the key in your pocket, but we're able to produce over 1,000 per plate per build. Each one of those builds takes about a day and a half. Those keys are broken off, blasted, and done. So small parts, quick time, high turnaround, high value pieces because there's internal passageways in those keys that you can't normally machine. On the other hand, here we have a lot of larger pieces, cylinder heads, transmission housings, the Bugatti brake caliper. Pieces like this that are much larger, you're going to be able to build one at a time. They might take 4, 5, 6 days to build, but they're higher value pieces. Performance. Is the performance met? So we're going to get into, this is a welding process. So this is what as printed looks like. You can see across, these are the weld beads being laid down. We have our hatch, we have our borders, and we have our fill contours in there. And as you can see also, there's a small little piece of porosity there. Porosity is the enemy of metal additive. We understand it fairly well, we can control it fairly well, but it's all about process control. Can we control the process well enough to prevent any porosity? So these are a lot of the important material properties of what we can do, and as you can see, a lot of what we're saying is this is going to be stronger than a casting. This will be stronger than any casting you get done, but 2 to 4% lower than wrought material in strength, hardness, density, 99.8% dense. There's no post-baking process with the metal powder bed process. This machine, these parts come out and they're fully solid. Qualifications. Is this yours? So, is this part yours? Is this part designed for metal additive? Yes, we can take a traditionally machined part, a traditionally cast part, put it in a machine and build it. That being said, if the vendor or the supplier says no, or the OEM says no, this part needs to be cast and machined, then you're going to have to cast and machine it. Parts need to be designed for metal additive. Not always can you just take a part, replace it with a metal additive process, and then keep on going. fairly simple one as well. Design, will it work? So we have a SO Systems video here. What's going to go in is the type of design changes. You can see this is a traditionally machined part, very simplistic. What we're going to be doing here is we're going to do 3 different iterations on optimizing this part for multiple different processes. So this part is going to be processed to optimized for casting, for additive, and then also for the best possible way to machine this part. And we'll be able to see here throughout this video how the changes happen. So you can see we're going to limit overhangs in additive manufacturing. In casting, we have a large open overhang there. They're able to cast that. Machining, very simplistic cutting edges, things like that. Post-processing, is this process painful? So, what needs to be done post-build? This is a plate. This part is actually sitting in our booth right now over in the East Hall, so you can see the difference from when it came out to where it is now. Some of the things that need to be done: quality verification. How do we know this part is good? We're not starting with a billet, we're starting with powder and then welding it. How are we going to do that? Is it dimensionally accurate? Stress relief. This is a welding process. Welds produce stress, so how are we going to relieve the stress in our part as we're doing this? Hipping. Does this part need to be hipped? Not all parts do, but hot isostatic pressing is a great way to close up any porosities and increase the strength of a piece. Heat treatment as well. Removal from the plate. How are we going to remove this from our plate? Are we going to break it off by hand? Are we going to EDM this? Is it going to be bandsawed? Support removal as well. How do we get this support off? This support is the same material as the material we're building with, so we can't just put it in a solution and dissolve it away. It needs to be broken off by either hand, systems, and everybody's looking for that magic bullet. And then surface finish. What's the required surface finish for the part you're looking for? Does part surface need to be machined? Does it need to be blasted? Does it need to be hand ground? Quality verification. So micro CT scanning is a great way for us to verify the internal integrity of the pieces. You can see here that this CT scan, we can see all the porosity through that piece right away. We don't have to cut the part open and look at it. We can see it through the scanning process. On top of that, also, handheld CMM for dimensional accuracy, or just general CMMing. The machine is scalable, so all material is going to have a shrinkage rate when built. So we can scale the material to the machine, we can build these pieces, and then afterwards we can verify that the parts we're building are the correct size. As well, here in the bottom picture you see that we also do metallography reports. So we have, this is our office, we're taking a look at a metallography report, seeing the microstructure of the piece and seeing, is this good material that we're building? And then as well here, X-ray scanning of internal passageways. So we're going to look and see, are those lattice structures good? Are those internal passageways good? Are we producing what we think we're producing inside of a piece without actually having to cut it open? Moving on to stress relief. So on aluminum, we build at about 200 degrees C. It's at or near the aging temperature of aluminum, so we don't really need to worry about it. But other materials such as titanium, Inconels, cobalt, chrome, we're going to build up a lot of stress in those materials, and those materials need to be stress relieved before we cut them off the plate. If we don't, those parts can warp. So either a argon blanketed stress relief furnace, or if you're using titanium or Inconel, we can move into a vacuum heat treat furnace as well. All of the time and heat is already well known. We know those kind of things, so we just got to base it off of what material that we're using. On top of that, hot isostatic pressing. So you can see here from an as printed part, there's a lot of porosity, a lot of small porosity, a lot of large pieces of porosity. What we're doing is we're going to put it into a system where it's going to apply a ton of pressure and a ton of heat and close up any of those porosities inside the piece. After that, we're going to move into removal from the plate. So you can see 3 different methods here. We have a wire EDM. So that's going to be, it's going to be cut off. You're going to use wire EDM to cut it off. This part that we just saw here, we're actually going to see a video of it later on, but that part was designed to just be broken off by hand. Snapped off by hand, it's aluminum, that part needs no post-processing, taken off, it's done. Or a bandsaw. Bandsaws work really well for cutting through support material, but if we're welding directly to a plate, an EDM is going to be a lot smoother finish, and it's going to be a lot more controlled finish. support removal from the plate. So you can see here, this is actually in their lab. This is my shop operator, Rick, and he's removing support. This is not a simple snap-off process. He's going to be working at this. He's going to be removing these supports. So now we're going to have to wonder, where are we putting these supports? Because they don't just fall away. If there's internal areas inside that part, he's going to have a really hard time getting in there and removing supports there. If you have closed passageways, say an engine block, we'd love to be able to print an engine block, but there's internal cooling jackets. How are we going to get the support out of those cooling jackets? They're not easily accessible pieces. This is here after the fact. You can see dirty process getting a lot of support off. Surface finishing. So on top of that, once we have our supports off, we're going to want to have a surface finish. Is as printing good enough? Do these need to be polished? So here we have a D-Light system. We've actually worked with them in the past. They actually do really good at electropolishing dental implants. You can see here that just over a 30-minute period of time, the change in surface finish between as printed and after the fact. And then examples. So these are some of the examples, and we'll walk through the reasons why these are good examples for the metal additive process. Here's a BMW piece. So this is a bracket that goes on the roof of the BMW i8 convertible. We print them on an SLM 500 out of aluminum. You can see he breaks them off. The part is nearly finished. There's no support needed. There's a couple finished machining passes for bolt holes, but it gets bolted onto the system. Now this is a good application because as we look at it, let's see, the size, yes, it fits. We can build a lot of these on an SLM 500. So does it fit? Absolutely. Material, it's aluminum, ALSI 10mg. Does it weld? Yes, it does. We're good. Economics, is there value in this piece? Well, this is a low production, high value sports car. So yes, there's value in this piece. Also, they couldn't do this any other way. The way this bracket moves and the orientation that it is, they were doing this in cast magnesium and it wasn't working properly. Performance, is it met? It's a fairly small bracket. It's a fairly small piece of the hood that's holding up, so there's not a lot of stress on it. So the performance is met. Qualifications, they designed this piece, so this piece does belong to them. So yes, qualifications. Design, will it work? Well, it's in production, so that's a simple one, yep. And then post-processing, is it painful? Not at all. That part, they break it off by hand, it's done. Not painful. I have another example here. So this one, SLM Solutions is fairly proud of. This is our SLM 500. It's building titanium right now. And as you can see, it's going to work through the process. As the process comes out, this is all our reusable, savable powder. It's going to fall away. The part's going to come out here, and it is the brake caliper for the Bugatti Chiron. So this piece is 2.5 kilos lighter than the cast aluminum piece. It's made out of titanium. It's being EDM'd off here. After a lot of black magic and hand finishing, here it is. This part is in testing. It's going into production next year for these vehicles. So, brake caliper, ALSI 10mg, that's the material that we need. Tensile strength. The tensile strength is met. The dimensions, it fits on the machine barely. It is a very large piece, but it does fit on the machine. 2 kilos lighter than the machined aluminum counterpart. So, does it need to be 3D printed titanium? Probably not, but they're saving 2 kilos per corner on a vehicle. That's a lot of weight, unsprung weight too. So that's efficiency, that's speed, it's a lot of things. Here's another piece as well. So this part is being built on as well on the motor bracket. So it has internal integrated cooling channels throughout the entire piece. It's made out of aluminum. It's made on the SLM 280 Twin. And it started in production in May 2016. So you can see they build 4, I think possibly 5 of them on a plate there. They have tensile bars, so they're doing quality verification. Every build, you want to do tensile bars, metallography bars, so they can go back and either pull those right away or check those after the fact and say, hey, these parts are good, these parts make sense. So, size, does it fit? Yes, and my video froze too, so that's phenomenal. Material, does it weld? Yes, so this is about the bracket. It was titanium, it does weld. The economics, is there value? The vehicle's $2 million, there is value. Obviously, this is high-level stuff right now, but this is a young industry. Performance, is it met? Yes, the performance is met and actually exceeded from the original cast piece. Qualifications, their part, their design. Design, will it work? It's going into production, yes it will work. And the post-processing, is it painful? For this particular part, the post-processing is extremely painful. There's a lot of support to be removed, but since it's a very low production piece, they're able to do that and take the time to do it. Here's another piece. A lot of people talk about heat exchangers in the metal additive process and the things we can do with heat exchangers. Heat exchangers are fairly efficient as are, but the end tanks, the stuff that typically could be cast and then weld on or even welded steel, these end tanks are designed and actually flow optimized so that we get equal flow throughout the entire heat exchanger. The heat exchanger itself doesn't need to be printed. It's a time-consuming piece. The end caps, those are fairly quick, fairly simple pieces and designed. So then we're able to optimize the heat exchanger as is and just weld on the aluminum piece right onto the thing, right onto the heat exchanger itself. So back to, again, to some high-value pieces. So we have a wing bracket in the corner there. We have internal passage, internal cooling on this piece. The flow control steady blow actuator, that's printed in all one piece. On the bottom corner there, that is high performance Porsche exhaust made out of Inconel 625. Those burn red hot, but the cars produce up to 1,400 horsepower, so really high performance pieces. And then here as well, so you can see the fan blades printed onto this piece. That piece doesn't look additive because it's not. That's actually a forged disc that's machined and surface ground, put into the system, and then we print the high value pieces on top of something that's fairly simple for us to build. So we don't need to build the very simplistic stuff. What we're doing is add it to the system and then printing the high value, highly complex pieces right on top of it. So for example, so we have some traditionally machined pieces here next to their additive counterparts. And as you can see, high reduction in weight. Parts that, you know, allow for overhangs that look fairly simple to remove supports on. This piece here, this is an interesting example. So this is actually a 4-into-1 DN40 vacuum fitting. That piece isn't produced standard. We actually make this piece for SLM 500s, but as you can see, there's a lot of support inside there that needs to be removed after the fact. So our guys in Germany, when they print these for our machines, have to sit there and break all that support out and remove it. They don't like it, but it's the only way that we can produce this particular piece. And then as well, that Dassault bracket, you see the original machine bracket, and now you can see the 3D printed bracket after the fact. You can see the weight savings there, you can see the reduction of material, and you can see that that part is printed with a very minimal amount of support because it was designed in so that support wasn't needed. And we're over in the West Hall, booth 2304. Do that one for the marketing manager, so. In summary, yet again, this is what we need to think of when we're building pieces. Does it fit? Does it weld? Is there value in what I'm trying to build? Is it met? Is it yours? Will it work? And is it painful? These are all things that SLM Solutions is willing to help you with. Please come to us with your issues, and in the application team, the group I work in, we will talk through it. We will figure out the part that you have, does it work? Are you guys able to build this? Does the machine make sense for you? That's what we do. That's all I have. Thank you everybody for your time. And questions. So Graham, if anybody has any questions, hand the microphone to him.
What kind of powder efficiency do you see? Because there's a lot more to suck in the parts that goes back, cleaning and all that.
So what type of powder efficiency?
Yeah.
In reference to the reusability of the powder?
Right.
Okay, so reusability of the powder. So when we're welding, we're producing some soot. That's about 2 to 4% of what we put into the machine is going to be lost. Okay. It's going to be oversized, condensate, not really weldable material. After that, we're getting everything else is going to be reusable. So we're looking at 98 to 96% reusability every single job of the unwelded material. And as far as performance, there's a lot of studies of 40 builds, 60 builds, 80 builds of the material maintaining fairly consistent material properties over the course of reusability.
And second question is the build plate.
Yep.
Because there's beads left on it, there's structures left on it. So what kind of materials, or how do you take care of that?
So the build plate is, it doesn't need to be surface ground. In shop, we just basically use a very simplistic Haas mill. We do an end mill, we just pass over it a couple of times. The plate's reusable. So after it's milled flat, there's obviously call out for parallelism and flatness within 50 microns. Once that's achieved, we can re-add the plate back to stock, put it back in, and then keep on reusing it. Yes, sir? Yeah.
You mentioned a 30-inch titanium fan blade.
Yep.
Is that just a trial that you prototype you made, or is it actually certified?
It's not actually certified right now. It's in development. It's a development piece, so we do have it over there. You can go take a look at it, but it is a development piece right now. Anything else?
So for aerospace materials, how far off do you think it's going to be until those the process specs are there where they think it's safe to put it up in the air? Because working in the aerospace machining industry, they have a lot of material-specific process specifications that have to be met before we even start machining it.
Yeah, absolutely. So before parts are flying in the air, that was a year ago. Airbus A350 has additive parts on it right now. They're flying. As far as structural components, that may be a couple more years off. So non-structural, non-critical flight components, those are flying right now as we speak. Structural components, obviously, this is a new process. You know, we've only been doing metal additive for 15 years. We've only been selling machines for less than 10. So FAA, you know, needs to get that comfort feeling before they're going to put critical components on an airplane up in the air. That may be a few more years off.
So most parts you made, you have to do the heat treatment, or not necessary?
Not necessarily. If the parts come out solid. If the requirements call for a heat treatment, then we will do it. But the mechanical properties of as printed are fairly decent. So if the mechanical properties meet as printed, we don't need to do a heat treat. On the other hand, stress relief sometimes needs to be done for materials like a titanium or cobalt chrome or Inconels, just because when they're cut off the plate, sometimes they do have a tendency to warp. Anybody else with questions? Okay, thank you all for your time.